I think Peter has mentioned that this indeed is a special day, and I think it's a special day for the department as well. And I will carry on in the introduction with the theme that Peter raised. But I wanted to show you this picture. This is one of our collaborators who has this way of drawing things, and in the fashion of Leonardo da Vinci. And he had this great idea for our physics design report to have a window. So I think what happened yesterday was that window has been opened. And this is he's an Italian, it's an Italian town. You can see the piazza here. The piazza actually contains a theory called supersymmetry. These lines are supersymmetry. And the Higgs boson to two photons is this one here. So there are all sorts of other things like these are, this is the ZZ, by the way, which I'll show you. And there are other peaks like supersymmetry, extra dimensions, Z primes, and so on. So that's what has happened yesterday. This window has been opened. So let me continue. So I'll just start with the summary of our results. So we have observed a new boson with a mass of 125.3 GeV at 4.9 sigma significance. This is the first time I think we see a boson of this type, so it is unique. Atlas also observes it at 5 sigma significance. So the fact that there are 2 experiments, and as I shall show you, these experiments see this boson in 2 different channels very clearly and at a similar significance independently. So there's a discovery. Now, Peter mentioned this question. This has been a quest which has been long. So it's almost 50 years from the time when the seminal papers were written. And you can see Tom Kibble is one of the authors of these papers. And in our references, so this is a reference of a paper that we published a few months ago, the state of the search for the Higgs boson, in fact contains 2 people from this department, Abdus Salam. Those are the first 3 references, which is the for the electroweak symmetry. And the second set contains 2 papers from Tom. Now, I think we also pretty associated in terms of the experimental work, and that has been a struggle of about 20 years. It wasn't obvious that these experiments can be done. So this is a copy of the first official document which was sent to peer review committee, and Peter Dornan was, I think, a member of that peer review committee. And this was written 1st of October 1992, so this year it'll be the 20th anniversary, and that was the first official document. Now, the construction and data taking of the experiment has taken about 20 years. These are the most complex scientific instruments I think ever built. And I will pick on a couple of detectors which have played quite an important role in the results that we saw yesterday, and I'll show you today. Imperial itself also has had a major impact on this experiment. And the first one actually is related to the first layer, which is a silicon tracker. We have about 200 square meters of silicon detectors, and that's more silicon detectors than all of the experiments so far in the world, including Atlas. The second thing, so that was the work which was pioneered by Jeff Hall with a couple of others. We had a big problem and was solved 10 years into the project. We had to change everything. So those were some of the problems that we had to face, and we succeeded. Another one which is that Peter has mentioned, which I pioneered and pushed very hard, and you'll see why that might be the case. The papers on this particular channel, which was considered to be quite a difficult channel at the time. So this is a paper that was written in 1990 in a conference which was looking at the LHC physics potential. And This work was done by two of us, Chris Sees. He's actually now leading the effort for the Higgs to gamma-gamma channel for CMS. And we already knew at that time that to detect this channel, we would have to have a damn good detector. And I think both Atlas and CMS detectors are, for this particular purpose, are very, very good. So let me go now to the talk itself, the standard model of particle physics, which is actually a culmination and a sort of a crowning achievement of 20th century science, one of them. It takes quantum mechanics and special theory relativity, along with all the particles that were discovered, and that has led us to this standard model of particle physics. And it's sometimes considered to be the periodic table of fundamental elements, and whether it is the final one, we shall see. Now, it contains, it's rather simple in a sense. Only the central element has been missing, which is this part here. All the other particles have been discovered. By the way, when I started with Peter, half of these particles had not been discovered. So you can see that a lot of progress has been made in the last 20, 30 odd years. So it states that matter is composed of fermions, and there are three families of fermions, which is the left-hand side. So these are the quarks, and these are the leptons, and we only need this first generation to describe the matter that we are made of, and everything around us is made of. The interactions are described by the exchange of energy, quanta of energy, and these are the bosons, the gluons, the photons, and the weak bosons, W and Z bosons. And it's a very successful description of physics at the scale of 100 GeV. In fact, I'll show you measurements that we've made at the energies of the LHC, and in almost all of the cases, it still is very precise. Now, it has been tested precisely many, many hundreds and thousands of times. I'll just show you one plot, and these are various measurements. At the bottom, you have 1, 2, 3 sigma away from the standard model prediction, and you can see it's very, very good agreement. Now, the problem has been that its basic mechanism, that of generating mass, was missing, and there's a field which is postulated, and the associated quantum of that field is the Higgs boson. The problem is we have electroweak unification, and the mediators of electroweak forces are the photons for the electromagnetic force and the Z and W bosons for the weak interaction. These two particles have a mass about 100 times the mass of the proton. This is strictly massless, and we don't know up till now how this actually happens. So that's what is called electroweak symmetry breaking, and that's the seminal work that people like Tom did. Now, there's another problem which comes up into the standard model. The Higgs boson is necessary actually to sort out some mathematical consistency problems in the standard model. This is a diagram, a Feynman diagram of WW scattering leading to Z production. And in fact, that's the matrix element, and there you have an S there. So that means that as you go up in energy, the phase space increases, and at some point, this amplitude and this process is going to violate unitarity. Probability is going to go beyond 1. And to regulate that, you postulate there's another particle which has the properties that the Higgs boson would have, and you get an extra term there. And when you add these terms, you regulate the problem. So this removes this runaway S, and the conclusion is that to preserve unitarity, one must switch on the Higgs boson, if you wish, at some mass, which is of the order of 1 TeV. And if we were to find it at about 100 GeV, then that means you can actually do perturbation theory, because 100 over 1,000 means the coupling's up at 10% level, and as you increase the order of the diagram, you can do something reliable and finite in calculations. So in brief, the Higgs boson with mass less than 1 TeV would complete the standard model, but it will bring a whole new set of questions, and I'll try to address some of those towards the end. Now, we also have some idea of where we were looking for even 20 years ago, and so the bet that had been made in pushing very hard for this crystal's calorimeter was that it would be living in the 120, 130 GeV range. in fact, there was guidance that from the virtual diagram. So these are loop diagrams. So this is the, if you wanted to measure the mass of the W or calculate the mass of the W, you'd have to take account of these quantum loops. And there's a Higgs loop and there's a top loop. And making precise measurements of the W and top quarks allows you to actually locate where the Higgs boson might be because of this logarithmic dependence. It's not a very strong dependence, it's logarithmic. And just a few months earlier, we'd narrowed down the region where the Higgs boson might exist, the standard model one, to this region here, 115 to 130 GeV. And so you can see that there'll be a tremendous consistency check, if you like, of also quantum mechanics in a sense, if we were to find the object in this area here. So now we had to, a little problem actually demonstrating that we could actually find this object. So this is the site of CERN, 27-kilometer circumference ring, 100 meters underground. There are 4 experiments, ATLAS and CMS. These are looking for the Higgs boson. The LHCb looking for matter-antimatter asymmetry, but also looking for new physics through these loop diagrams I was mentioning. So we'll have to actually bring in a complete picture as well. So those experiments also play an important role in what is to come. And Alice looks at the quark-gluon plasma and so on. So the accelerator in brief. So what happens is the protons are accelerated by superconducting RF cavities in a manner where a surfer is accelerated by a water wave. These are electromagnetic waves, and the particles surf those waves, and they're guided around their circular paths by powerful superconducting dipole magnets, a real engineering challenge. And that has facing that challenge has allowed us to have the LHC, if you wish, at the energies it has at the moment. The dipole magnets operate at 8.3 Tesla in superfluid helium. So you can see the word superconducting, superfluid, all sorts of things. All of these are quantum phenomena, as you know. And CERN has the largest refrigerator in the world. It's 120 tons of superfluid helium. And it is a very interesting engineering material. So a lot of engineering has gone into the accelerator and the detectors, which I won't have much time to develop on. Now, let's look at the collisions. So you have to have proton-proton collisions. The protons are organized in bunches. The bunches actually, this is an old transparency, has something like 100 billion protons. At the moment, as we speak, they're probably putting something like 170 billion protons. So the machine has gone beyond design already in this particular parameter. The energy is about half the energy there. And the luminosity is very close, meaning that we are getting something like 600 million interactions per second. And so the protons interact head-on. In fact, it's the constituents of the protons that hit head-on, which are the partons, the quarks, and gluons. And they make the Higgs boson. So the Higgs boson, if it were to be created, could decay into ZZ, 2Z particles, which then themselves decay into electron, positron, or a muon, mu plus, mu minus. Now, to give you an idea, this kind of particle is made 1 in 10 trillion proton-proton interactions. So what you will see are data from about 700 trillion proton-proton interactions. So we're talking about a handful of events. So that is another challenge which we had to face. We knew about it at the time when we were designing it, and those were where the extrapolations to technologies that might exist 15 years later came in. Now, the search for this Higgs boson was also something which actually drove the design of the experiment. Peter and I have mentioned this area here. This is where we expected it, and its width is very narrow. It's a few MeV, and it has mass of 100 GeV. So you are completely dominated by the instrumental resolutions, energy and mass resolutions. So you had to devise an instrument that could be the best you could get to, so that the peak, if it were to appear, would be as narrow as possible over a large background, as we shall see later. I will be concentrating on these two decay modes, but the theory did not predict the mass of the Higgs, and it could have been anywhere, it could be anywhere. The favorable decay modes obviously change with mass, and this is indicated by this diagram here. And this is actually a transparency from the 1990s. So this is a CMS detector. It is dominated by a very high field solenoid, 13 meters in length, 6 meters in bore. Contains the first 3 layers, the inner tracker, which tracks charged particles, the second layer, which is the electromagnetic calorimeter made of lead tungstate crystals, which measures the energies of the photons and electrons very precisely. The inner tracker has this 200 square meters of silicon, split into pixels, which have a size of about 100 microns by 100 microns. So we can track particles to precision about 15 microns and very high momentum resolution, which is very important, as we shall see later. And on the outer layer is the muon system, which also has played quite an important role in the results that I will be showing you. So this is sort of a cylindrical onion which was sliced into 15 pieces. The objects were assembled on the surface and then lowered 100 meters underground in pieces, and that took something like 1 year, although each slice takes about 1 day to lower. So this is the experiment closed, and so you can see the cylindrical aspect, and that's the beam pipe. And we first closed it in 2008, we opened it in 2009, it has been closed ever since. Now inside there are objects which, if something goes wrong, we would take something like 3 months to a year to open and repair. And thank our lucky stars, nothing like that has happened, and the experiments are actually working extremely well. So I don't know, this is not going to come out very well. So this is the cylindrical onion, and this is an animation of bunches of protons coming in. There's a hole left to let the beams in and out, and these are the layers of the detector, and that's a proton-proton collision. And this is a reconstruction by computer reconstruction codes of what has happened. So you can see there's the enormous numbers of particles which are produced, and each one of them are identified correctly. What you see is the first 3 layers in the colors. The first one, the yellow one, was the inner tracker, which tracks the charged particles. So we have to have we have 600 million proton-proton interactions taking place every second, and we select about 300 most interesting ones. And the way we do that is to look for energy going at 90 degrees, large amount of energy going at 90 degrees, because those are the sort of violent collisions which might contain the objects like the Higgs boson. This picture, in fact, is of 2 photons, and there are a couple of characteristics which I wanted to point out to you here. So the beams come in this way. There are quite a few charged particles, and these charged particles allow us to locate where the vertex would take place, because it's a neutral system. And the way we're running at the moment, there are about 30 to 40 pairs of protons which are interacting in a space of this length, and we need to know the right vertex from where the photons came. Otherwise our mass resolution gets affected. The other thing that this picture shows is that we are looking for a process which is fundamental. So in fact, I'll show you a little bit later, it's the quarks and the gluons which interact, create the object, and that object disintegrates. In this case, it's disintegrated into 2 photons. And these photons come from the primary partonic process. There's nothing else around it. Photons can come from other things which have stuff around it. So we look for photons with nothing around them, nothing very much around them. We call them isolated. So that is an important criterion of showing that something fundamental has taken place. The interaction is fundamental. Of course, this leads to huge amounts of computing, and that is where the data have been processed, about 100 petabytes of storage per year. So that's the collaboration itself, which is very large, and it has about 3,000 scientists and engineers. What I wanted also to say before I go into the physics is that the team at Imperial is quite large, and it has actually played a major role in the conceptual design, in the radiation-hard electronics, the electromagnetic calorimeter, the trigger systems, the computing, and the operations nowadays. We're also thinking of the future as well, because these experiments are going to continue for about 15, 20 years, and the physics. So we've been spending a lot of time. Half our group is working on the Higgs boson, half looking for symmetry, supersymmetry. And this is the list of people. And one other thing which, before I go into the science, is that these kind of endeavors do require constant support and backup over a long period. And that's not only group leaders, and Peter has been particularly helpful. For a long period, he was the group leader, and now Jordan, and also the physics department heads. I think they have been very understanding for letting me off sometimes, and I hope that continues. and the deans and the rectors. And many of them actually have been to the experiment and seen what we are doing. Next year, the experiments will be open, so people want to go there can have a look at that. As I said, the experiment is working very well. So over 99% of the channels are working at the design performance. We have a very high data taking efficiency and recording efficiency and validation efficiency. This is the numbers of after data recording and then making sure everything is working. So it's about 90%. Now, this is a plot that you will see several times in future, and we use a word called inverse femtobarns. So I'll be talking about many places as 5 inverse femtobarns of 2011 data and 2012 data. What it means is that we have examined 400 trillion proton-proton interactions taken last year and taken so far this year. So we have had 800 trillion proton-proton interactions. That's the data I will be showing. But we'll be using the words 5 inverse femtobarns. So when we look for new particles, we have actually to see what comes out. So the Higgs obviously does not come out. It disintegrates immediately. In this particular case, there's an event where you have a ZZ being produced, and one of the Zs has gone into an electron and a positron. That's the first layer, and the second layer in red. And in this case, that electron is isolated, and the height of this tower actually gives you the energy that has been picked up by these crystals. So the Z boson has decayed into an electron and a positron pair. And in this case, it's the muon system, the fourth layer, plus the inner tracker, which has declared itself. And the Z has decayed into mu plus, mu minus. So in fact, all of the particles actually decay into the particles which we are very familiar with. So quarks obviously appear in our detectors as collimated bunches of particles. We call them jets. And you can see clearly the jet structure here. So these are the collimated bunches of particles, and they're coming from quarks and gluons. And if you want to detect neutrinos, clearly there's an imbalance. You project everything onto the transverse plane, and if there's something missing, then you know there's a neutrino gone by, because the protons come in, they have 0 transverse momentum. The interaction can move this way or that way depending on how much energy of the proton from this side of the quark has carried, and it's usually a different one from the quark and gluon, so the system can move longitudinally but not transversely. So we work in transverse directions most of the time, because the initial state has 0 transverse momentum or energy. So now a few transparencies of the performance. So this is a Z boson, so you can see that in fact with 2 jets. And so the fourth layer, the muon system, has spoken. There's something in the inner tracker. You combine these things and you measure the momentum. So you measure the momentum and you create a quantity called the effective mass. So you take the energy and direction of these muons, and oftentimes it can come from background processes or something like a photon which doesn't have a particular energy, a virtual photon, or it can come from a particle. In the picture that I showed you, it came from a Z boson, and there you would see a large number of such events accumulating on this plot of the effective mass. Now this plot came out about 2 months after we started running in 2010, and this contains essentially the history of particle physics, because these are etas, rhos, omegas, and phis. These were the sort of particles I'm sure Peter was working very hard when he was doing his graduate studies. I came in around about this time when this particle was discovered, so that's the charm, and psi prime, and this came a few years later, the upsilon and the Z, which was about 30 years ago. Now, by looking at this plot, we can also tell how well the detector is performing, because the width of this if you blow this up, you see this. The width is about 67 MeV, and our design goal was about 70 MeV. So this actually tells us a lot that the detector is performing exceedingly well. So let's go to the science now. So the LHC was conceived to look for new physics. And this new physics has this list here. So elucidate the mechanism of electroweak symmetry breaking, look for supersymmetry. Can the nature of dark matter be revealed? Extra dimensions, compositeness, you always look for that. And unknowns. So these are the known unknowns, if you wish. And there could be unknown unknowns if you now go and listen to a particular Secretary of Defense of the US. But we can use that phrase. Now, of course, these signals can only be claimed after understanding the standard model processes. So what I'll show you later on in the talk actually sits on the work that has happened. There are hundreds of papers we have published of very many standard model measurements of all types. QCD measurements, electroweak measurements, and they're all consistent with the standard model. I'll just show you a couple of plots. So that's a prerequisite to go there. So one way to also look at this, the collisions that we have been examining. So if you don't have a very large number of collisions, you have to sit in this area here. So you look at the BB bar production, which is very prevalent. So we actually are looking at, I mentioned the word femtobarn. So we're in this area here. So we have to go, we went down from there to there in 2 years. So initial papers were written on general properties. Then about a year ago, the papers started talking about the standard model physics, W production, Z production. And this now is a rate where we actually are throwing them away. We don't even record them because the rate is 300 hertz and we have to cut off here. And this is where we are now. So you can see we're looking at things which are orders and orders of magnitude rarer. So this is the Higgs goes to ZZ, and this is the gamma gamma. And they are processes which have femtobarn type cross sections. So now let me just give you some idea of the hard scatter that occurs. So there's a quark gluon, which actually has led to a photon and a quark. Now this gluon could be a photon, and that could create background for the channel that I'm looking for. But what we, as I said earlier, what we're looking for is that from this hard scatter, this photon, for example, is isolated. There's no energy around it. So this actually tells you something about the types of processes, and isolation is a criterion we use a lot. And typical thresholds are about 20, 30 GeV in transverse momenta for the objects that we shall be using. So that's the purpose of this diagram. So now let's look at the quark and gluon production, jet production, and see how it compares with the predictions of quantum chromodynamics. So the data points are obviously points, dots, and the predictions are the lines. And they're about 8, 9, 10 orders of magnitude. And they're different angular ranges. So you look at jets, this angular range, that one further down, and see what happens, and whether they are consistent with the theory. And in fact, they're extremely well matched. And this is the a dimuon spectrum. So we're looking at dimuons of 1.5 TeV here in this endpoints here. So here we're looking for another resonance. If there were, for example, a Z prime of 1 TeV, it should show up here as another peak. It hasn't shown up, so we can actually place limits. So this actually tells you how well the detector is performing, and this is a compilation of only the electroweak measurements. So you can see here as well, there are about 5 or 6 orders of magnitude of rarity which have been reproduced well by the detector. So let's go to the search for the Higgs boson now. So we understand the known physics extremely well, and it is being reproduced correctly as predicted by the standard model in our detectors. So the detectors are physics commissioned. Now, when we're looking for the Higgs boson, or for that matter any particle, there are certain things you have to do. You have to look at the production cross-section. How often is that object produced? That's the first thing. And how does it decay? How many times does it decay into 2 photons, for example, in our case, for the Higgs goes to 2 photons? And what is the selection efficiency? What is your efficiency of actually reconstructing the photon? And what is the mass resolution? So if you've reconstructed the direction and the energy of the photons, you create this quantity called the effective mass. And if there was a narrow peak with the, let's say, 0 width, how wide would it appear in your detector? And the level of backgrounds. And they're predominantly from the standard model processes. And that's why the previous section was very important. So in looking at the production rates, so these are the cross sections, and the most prevalent production mechanism is where you take a gluon from a proton, another gluon from a proton, and you have a quantum loop. And that loop is the top quark, because the Higgs likes to couple strongly to heavy objects because it gives mass. So the coupling goes as the mass of the quark squared almost. So the top being the heaviest is the one that it picks up. So it's quite a virtual loop. And the next one is the WW scattering, so the scattering that I talked about right at the beginning. So that's the next process which has this. So in the data that I'll be showing you, we should have produced something like 250,000 Higgs bosons. And I'll be showing you plots of hundreds or tens. So that's what ends up in the final plot, because there's another step which I'll go to the next transparency. So also the calculations actually tell you, the thickness of these bands tell you the accuracy of the calculation. Now you produce the object, it has to now decay and manifest itself in our detector. So let's concentrate on just this section here, because that's the area that we're most interested in. And it goes into BB bar about 64% of the time. Completely useless to us. We can't do much with it. So we have to actually select very rare types of topologies to even start looking at that kind of stuff. But what we look for are on the bottom end here. So we look for the gamma gamma. It's 2 per mil. So you produce so many, but only 2 per mil actually go into photon-photon mode. And that mode itself is also a loop calculation. It's a loop process, because the Higgs then could disintegrate or create TT bar pair, which then radiates off a photon, or a WW pair and radiates a photon. In fact, this particular process dominates over that one. And this actually also tells you something very important about this particular process, and I'll allude to it later, that if there's something else going on here, for example, if there was an extra W or a heavy charged particle, which is a boson, then this decay branching fraction, if it doesn't come out to be 1, would be telling you something. There's something else going on which we don't know about. So these quantum corrections do play a very important role in our measurements. So let's now go to the measurements, and I'll pick on 2 channels. So this is the decay modes, and that was the production mode, so the 2 transparencies that I showed you. And we have looked at all of the places where there are ticks there. And when we combine the data, as I'll show you, it's a combination of all of these channels which have been looked at. And the BB bar is still there, but you have to go to esoteric topologies like the TT bar, which has a cross-section which is about 100 times smaller than the most prevalent one, which is this one here. But it's clean. So I will be concentrating on the ZZ to 4 leptons and the gamma-gamma mode for this colloquium. The reason being, at low mass, as I said, the width is very small. The instrumental mass resolution plays an important role and a special role. And these are the modes that have the best mass resolution. So if there are any peaks, we shall see them there first. Now, this was the state of the affairs at the end of last year. Anything below 1 is excluded at the level of 95%. Anything above there could be something happening. So this diagram was indicating that there was something happening somewhere between 115 and 130 GeV. So that was the situation, and we said more data are needed to ascertain the origin of this observed excess, which is a small excess. Now, so what we then did was, we knew we had to concentrate in this area, so we started re-optimizing our analyses, changing some cuts, taking account of the fact that we increased the number of events occurring in the same crossing from about 10, 12 to about 20, 30, which we had to take into account. And we optimized all of the cuts on what we expected. So if the expected sensitivity improved, that was a cut we would use. And we did not look in this region here. So that region was blinded, we call it. So we didn't look at it until 15th of June, which is when I got very excited. Now, this is what it means. So we did not look at this area. This is a gamma-gamma mass spectrum. So we looked at this part, that part, and checked everything is functioning well. And on 15th of June, we opened and looked in this area here. So that's what it's showing here. In fact, the sensitivity of the analysis of the gamma-gamma and the ZZ, which I'll talk about, was very high. And there's another one which I shall not talk about, which is equally high. So one thing I also want to tell you about is I'll be using something called the p-value. The p-value is a probability that in the absence of a signal, that a background fluctuates to give you an excess of the amount that you have observed. So this is what we use to optimize the analysis. And so we optimized it, and finally we combined everything, and we said, so what is our sensitivity? And it turns out that our sensitivity is 6 sigma, very high. So that was a little bit of a surprise, because the optimization obviously had worked very well, and there were some new techniques brought in with the multivariate techniques, which I'll say a few words about. So if you see something, if we were to see something below 6 sigma, then we've seen a downward fluctuation of an object if it was there. If you see above that, then we were lucky. When we're making discoveries, you can have both ways, and you tend to be a little bit on the lucky side to make the discovery, because you get a little bit of preferential treatment. We didn't get it, by the way, because the expectation of the ATLAS experiment is 4.6, so much lower than ours, and we shall see what the result was. So the point I wanted to make was that you can have fluctuations upwards or downwards, and so when we look at the data, in some cases we'll have a downward fluctuation, sometimes you can have an upward fluctuation, and that has to be taken into account with the limited statistics we've got at the moment. So that was actually the reason for doing it, but anyway. So let's look at the gamma-gamma. So this is what a gamma-gamma event looked like. It's one of the candidates. So you can see here that clearly the 2 photons, and the height is giving you the energy, and the protons coming in, and there's not much else going on around the photon, certainly. So the idea is to search for a narrow peak in a diphoton mass distribution over a large background. The signal to background ratio is about 1 in 10 or 1 in 20. And the background essentially comes from QCD processes, for example, QQ bar annihilating to give you 2 photons, just like an electron-positron pair annihilate to give you 2 photons, and some other loop diagrams. There's another component, which is the a reducible background, which I indicated to you, which is dealt by using isolation, because the quark fragments into a photon, but normally it fragments with many other stuff around it. So we actually started using some techniques which try to improve the performance, so the first one is how do we actually measure the energy? The calorimeter that we've got has boundaries in it. It has support structures in it, gaps in it, material in the gaps. So if the photon were to hit there, then we would actually know that we have perhaps lost a little bit of energy. So use Monte Carlos and check whether we have to correct, by how much we have to correct the energy if the photon were to impact in that particular area. And as a guide to check that we're doing the right thing, we do the same thing for electrons, for example, and see whether the peak, the width of the Z peak, which we know very precisely, narrows or broadens. If it narrows, then we're doing the right thing. If it broadens, we're doing the wrong thing. So that's how you check that the procedure that you're following is correct. Now, there are other things which we also use is the distribution of the photons. The Higgs boson has a slightly different distribution from the QCD processes. You bring that into account. And you also look at the event resolutions and many other criteria of that nature, and you put them into a melting pot and then get an answer out. Another problem is the number of vertices. This is one crossing. There's about 40 vertices in here, and we've got to select the right one. And we do that by looking at the number of charged particles going out carrying a high PT, for example. A higher PT tells you that that is more likely to be the interaction vertex of interest. By mixing everything, you create what's called a MVA output, which runs from -1 to 1. For the signal, so this is the gluon-gluon fusion process, it looks like this. The QCD background, it would look like that. So what we then do is to make a cut here, and we look at those events. This is mostly background, and there are 4 categories, and the further to the right you go, the higher the signal to background ratio it is. So we then make this cut and then look at what happens. So if you're looking for a peak, you need to understand how to fit the background. So we have 3 methods of doing that, 3 different methods, 3 independent sets of people. And this transparency contains a lot of work from the Imperial College group, in fact. So we've been working on essentially all of these analyses. The simple one, which I'll come to a little bit later, but let's look at the first one. So you've got that output, you've got a selection of events, and here what happens is that you fit a polynomial, and the order depends on the numbers of events you've got. So you fit the polynomial, and then you look for a bump. In the second case, you actually remove the region where you're thinking the signal would be, and you look at the measured background on either side of that, and then you slide that region and see if you see a peak that way. And the third one is uses another different method, completely different method, a more traditional method, where it separates out the photons into areas where they go into the central region and the forward region, whether they have converted or not converted. So very simple categories. And all three methods actually give you consistent and the similar results. So this is a pretty robust result. When you do that, you produce such a plot where this is what would the expectation. So if you have an excess, this will go way above here, and the excess is characterized by this p-value plot, and from there you can read off 4 sigma. So we have a 4 sigma signal inside the gamma-gamma mode, but you can also see there's a secondary peak there, because there's another aspect which is sometimes called the look elsewhere effect. This plot actually shows you the look elsewhere effect because there's something else around there, because the mass resolution is very good and you look at very many bins and the signal could fluctuate in any one of them, and there's a certain probability of that happening. So this actually is quite an interesting plot. And so then you go back and you collect all your events, weight them according to the signal to noise in the 4 categories that I mentioned, and you plot them. And that's the plot that we saw on the 15th of June. And clearly you see a bump. I was astonished because I didn't expect to see this bump so early, because I was thinking that we needed a lot more data, and that will come at the end of this year, not in the middle of this year. So that was a really very pleasant surprise. And so this is the expected 2.8. So we had a beneficial upward fluctuation, or it's something else, or the standard model is or the Higgs boson is singing a bit more loudly than the standard model would predict, or whatever this object is. Now, the fitted strength is about 1.6 times the standard model, but the error bar is very large, so you really can't deduce very much from it. And the particle is seen in the diphoton mode, so that tells you that it has to have a spin 0 or spin 2. We can't actually just as yet tell whether it's spin 0 or spin 2. And the next set of measurements, we will be looking at whether it's spin 0, whether it's a scalar or a pseudoscalar spin 0 object. As I said, we've never seen a fundamental spin 0 object so far. This is the first one. This is the Atlas result, and so they've had a similar upward fluctuation as us. So 2.4 goes to 4.5 observed, and there again you can see the peak. So this is really very, very striking evidence. Now let's go to the 4-lepton channel. So we're going to do the same thing, but the number of events that we're going to expect is going to be much smaller, because you've got to produce the Z, and the Z then has to decay into E plus E minus, and that happens in the case of E plus E minus or mu plus E minus only 3% of the times. So if you have 2 of them happening, so it's like something like 1 in 1,000 of those events will end up that way. So we are going to be looking for at very few events. So, but they're very clean. There's very little background, apart from background from the calculable processes, and that we know is very small. It's very difficult to mimic this topology through standard model processes, apart from this fundamental process, which is a very low cross-section. So we can estimate the background using simulation, and we can look at the reducible backgrounds that can happen from other sources by using some data techniques where you loosen some cuts and see what happens. And that's the result. So in fact, the Z boson can also go into 4 leptons through this virtual process, where it has one of the muons has radiated, for example, a photon, a virtual photon, which goes into mu plus mu minus pair. So you get 4 muons on the Z pole, and that is very, very convenient, because it tells you that you actually understand what's going on. This is a process which is calculable to great accuracy. And the width actually tells us what sort of resolutions we are expecting, and whether that resolution is as our simulations are giving us. And so it's a very, very powerful cross-check. And that's where we're seeing the bump. So we're seeing something like 10, 11 events where you expect something of order of 4 or 5. There's very little background. And down here are the errors of individual events. So these 2 events here are very, very tiny error. These type of events going to 4 muons. Our momentum resolution is very, very good, and gives us just these two events actually dominate the mass measurement that you would make out of this. So if you were to get some like 20, 30 of those, that would be really beautiful. So I didn't need to tell you that. Now, one other thing that happens is that the sort of measurements we shall now be doing is to look at the angular distributions and whether they are consistent with what is predicted for a spin-zero object, which should be essentially isotropic. But in the case of the ZZ, you can actually have two planes because you have the electron-positron from one or a muon pair from the other, and these planes can have different angles with respect to each other. The Z's are traveling, so you can make certain angles. In this case, the angular distribution is with respect to the negative of the lepton pair. And so you make an angle which is θ1, which is shown here. So you can see the standard model Higgs boson has quite a different prediction from the background. And you can also look at the effective mass of the second pair, the lower mass pair. And that again looks quite different for the standard model compared to the standard model Higgs boson. So again, you use multivariate techniques, and you get to these kind of plots. Half of the power of the significance of this particular channel comes from angular information. The other half comes from the mass information that I showed you. So this is what happens. So you get a MVA output from 0 to 1 this time. And this is what the standard model Higgs boson would give you. That's the background. And so the background should be more populated in this area. So if you were seeing a signal, they should be in this area here in terms of mass. So this is mass versus this variable called Mela, matrix element variable. And so let's see what happens. So that's the background. So it's reproducing the previous plot with just now the events as we see them. So you can see that where you don't expect anything from background, we're getting a population here. And if you now say what would the signal look like, and that's what the signal would look like, and you can see it doesn't quite perfectly fit, but it's the nature of things when you have low statistics, or it's telling you something interesting. We can't tell. So you can see that this is another element that goes into saying that there is something signal-like going on, which seems to be consistent with the expectation of the standard model Higgs. So again, you do sort of similar plots and a p-value plot, and the bottom line is the expected significance is 3.8, and the observed is 3.2. So this has lower strength, slightly lower strength. And in the case of Atlas, they expected 2.6, they see 3.4. And this is the peak there. They see 13 events and expected 5. So I've dealt with 2 of the channels. We have 5 channels and many different modes. And so what we're now going to do is to put everything together. And I won't go into the details of the other channels, but we now combine all the information. So CMS combines several combinations, but we only report all of the 5 modes, plus the ZZ and the gamma-gamma mode alone, which are the high mass resolution modes. And Atlas combined their ZZ and gamma-gamma mode from 2011, 2012, but they hadn't finished the analysis for the other channels, and they combined with the other channels last year's data. So let's look what happens. For the gamma-gamma, plus the 4 lepton, which are the high resolution, high mass resolution modes, we expected 4.7, and we saw 5. So it does also depend on which combination you take, what exact value of the observed significance will be. But when you do these kind of things, you have to say, before you do the analysis, that's the one I will base my result on. So the result was, we said we would base our result on the full combination. So that's the next thing. The full combination, we expected 5.9 because it's a lot more sensitive, and we see 4.9. And Atlas expected 4.6, and they saw 5. But the trend is the same. So we see the signal in the same place in 2 different channels, in 2 different experiments, and 2 different types of technologies for the calorimeter. We use a crystal calorimeter. They use liquid argon, completely different systematics and differences. So let's look at the properties of the new particle. The first thing you want to know is what is its mass. So what we've done is we've separated out the gamma-gamma channel into what we call the vector boson fusion, where the WW are radiated of incoming quarks. They fuse, create the Higgs boson, and then decays into 2 photons, compared to the gluon-gluon process, because they could be different. So we've left them different, and the statistical accuracy is not very high, and the ZZ and the gamma-gamma. And so you let the strengths float as they wish, and you get a value for the mass. And the Atlas value is 126.5. And within the errors that we're quoting so far, I don't think that's an issue just as yet. Now, the next thing you want to say is that if I combine everything, does it look like the standard model Higgs boson or not? And it turns out that the strength that all of the combinations would require or demand is 0.8, 80%. But the error bar is large, of 20%. So again, fits. The other thing you can say is, okay, now let me look at the strengths of the individual channels. I showed you the strengths of the ZZ and the gamma-gamma, but there are other channels which have been looked at. And this is the Atlas stuff, and that's the CMS stuff. And you can see the gamma-gamma is high, but the others are a little bit low, below the line of 1. But within the errors, you can't really tell. So we're going to be taking about 3 times more data, because the run has been extended by 2 or 3 months. And so these kind of measurements will start becoming critical if they agree or not by the end of this year or beginning of next year. So I also wanted to show you a plot where the Tevatron results, which are also shown on Monday, indicating that they're dominated by the BB bar production mode, which is a rather difficult one for us, so it's somewhat complementary. And for them, the BB bar is actually singing more loudly than the previous plot, for example. So that's also something to be borne in mind. So we're in the realm of not enough statistics yet to draw conclusions. But of course, to give you an idea of what else is coming, we can start looking at the couplings. Now, there's a table here which is quite complicated. These are the decay modes, and these are the production modes. Let's just concentrate on this box here. So that box here, and just let's look at only this term and that term, and forget the rest. So that term comes from the fact that you have a fermion in the production loop, so that's CF. So it goes as CF squared in the intensity. This is the amplitude. And then it decays into the WW. So the WW is a vector boson, so you have an alpha times V, but as I also indicated, this process can have a top loop here, and that's the fermion, the beta fermion. So you create all of these things, and you do all of things, do the fitting. There are only 2 parameters. In fact, you can put parameters for the top, for the bottom, and that's the next step of the things. But for simplicity and the fact that we don't have enough data, we just parameterize the 2 parameters, and that's what we get. In fact, you probably can't see it. This is value of 1. That's where the standard model would be, 1, 1, in this space. And we're seeing it at 1.5. But the 95% ellipse covers that, so it's not something that we should worry unduly just as yet. But that's the sort of measurement that will tell us whether this is indeed a standard model Higgs boson or not, or whether it comes with some other partners. So this is a summary. I won't go into that. Now let's look at the prospects a little bit. So last 4 or 5 minutes. Even if the Higgs boson exists, all is not completely well with the standard model alone. And that is a statement that we were making 20 years ago as well. The next question is, why is the Higgs boson mass so low? It is quite high, 100 GeV, but it's quite low. And the reason is this. The Higgs boson, in a sense, puts a drag on things. It resists, particles resist and acquire mass. It itself resists. And in fact, it resists so much, it should resist so much that its mass should be almost infinite. And that's due to the fact that it gets loop corrections. And in the loops, you have momenta running, which go from the R scale to the next highest scale. If that scale happens to be the grand unification scale, which is 10 to the 15 GeV, so you see an object of 100 GeV gets a correction of 10 to the 15 GeV, complete nonsense. So either there is a new scale or there's something else happening. And the favored mechanism usually tends to be supersymmetry, because for supersymmetry, for every loop you have a loop with the, for a fermion loop, you have a boson loop. In quantum mechanics, they come with opposite signs, and if the mass differences are not very large, they cancel. So 100 GeV remains 100 GeV and doesn't get these corrections. But you can't have that scale go very high. So that's where supersymmetry comes in. and it predicts a doubling of all known particles, but it also has something else. It predicts 5 Higgs bosons. And the lightest one, this one H0, would have the properties almost identical to the standard model Higgs. It would be subtly different. So the precision measurements will tell us where we sit. And this lightest particle of its species could explain dark matter. So let me just finish with that, and just sort of perhaps not in too serious a manner, say a few things. This is a picture, and this one is actually serious. This is a picture of 2 clusters of galaxies colliding. This is a bullet cluster. I think our astrophysics friends would know this very well. And this is a composite picture taken by Hubble optical and Magellan optical telescope, and the Chandra X-ray telescope, and using Hubble gravitational lensing. So the galaxies have gone the right way through. The red stuff from Chandrasekhar is the hot gas, which is normal material, which has interacted and has stayed put, essentially. The blue stuff is from gravitational lensing, contains 10 times more matter than what's in the red. And that has gone all the way, right the way through. And that is exactly the sort of property a dark matter particle, like the lightest supersymmetric particle, has. It's a weakly interacting massive particle. So this is some sort of a circumstantial evidence that particles of that nature would be responsible from cosmological considerations. The mass is thought to be of the order of hundreds of GeV. The last one is the WMAP measurements, very precise measurements, which are indicating that the universe is flat. So that indicates that the matter that we are made of, that we see the visible matter, is about 5%. The dark matter is about 20 to 25%, and the rest is dark energy. And that dark energy gets confirmation not only from WMAP measurements, but also from the supernova measurements, for which the Nobel Prize of Physics was given last year. Now, one of the intriguing questions, which I always used to be saying, is that if you were to find something which was a fundamental spin zero massive boson, then they have a property which appears to be repulsive if you have a collection of them at certain energies. And that would then lead to something which could be responsible for this acceleration or for inflation in the early universe. So some people actually say that the remnant of some elementary scalar field analogous to the Higgs field would be responsible. So I think we have to understand what we have observed, I believe, is very fundamental. And what it is, we've got to find out. And I think it will have quite deep consequences in our understanding how nature works. So outlook for the LHC, we have observed a state that looks like the standard model Higgs boson, but the question is, does it behave like one? Is it alone in this new species? And the LHC run has been extended and will triple the current data set. We'll start measuring the properties of this new particle, and the LHC will move to the design energy, which is 14 TeV, twice the energy, in 2015, and we'll continue the work to elucidate the true nature of this new boson. And we'll continue to search, as we are doing now. Only about a third of the collaboration is working on the Higgs physics. The others are looking for other things. About a quarter are working on standard model measurements still, and the others are looking for new physics. And the new physics can come up in various guises. And we continue looking for the unexpected as well. And I think I see it as an incredible journey, certainly personally also, starting about 20 years ago. It has been a big struggle, although probably it doesn't come across that way. We had plenty of problems of all sorts of nature, technical, financial, managerial, you name it, and we've had it, companies going bust, processes dropping out. We had to make mid-course corrections of huge proportions, but it all came together in the end. So the second part, I used to say, of the journey has started in earnest. I think the most exciting part of this incredible journey has started now. And the physics exploitation will take at least a couple of decades. So any guys want to do PhDs in particle physics, There's great stuff to do now. And I wanted to end with a tribute to, I think Peter mentioned Michel. We've been colleagues who worked for many years, first in UA1 experiment, and we actually were the two leaders of the CMS experiment from conception to first data taking, spanning some like 17 years. He's actually a visiting scientist in our group, and he's also been working on the ZZ, making sure the ZZ results are correct. Oh, sorry, the WW results are correct. And I think I'll stop here, and I'll take questions if there are any.